Thanks, Yukka. Hello, I'm Abhishek Deshmukh. I'm team lead of application engineering at Quansant. I did my PhD in multi-phase flows and turbulent combustion. And today we'll have a look at the more advanced example on harmonic balance. Um, yeah. So, uh, so the use case that I have chosen here is from this open access paper from 2021. It's based on the microspeaker, so newly emerging applications of um, MEMS actuate or uh, electrostatically actuated MEMS devices. And yeah, so the microspeakers are one of them, which are silicon based and electrostatically actuated. The reason for going for this technology is to have a wider frequency range and also dynamic response of these speakers. And one of the challenges that these let's say these fabrication or even the operation of these MEMS actuated microspeakers is the instabilities, for example, pull-in instabilities and unstable equilibrium. Um, so in order to design these devices, one needs to perform some kind of simulations to gauge the response and um, response of the design. So let's move on to the setup. So in this case the setup is quite simple. There are two parallel plates which are separated by an air gap. One of the plate is fixed, and the top plate is able to move. Basically it can deform in one direction, and as I said, so these are actuated by electrostatics, and this is done by applying voltage on the top and uh, between the top and bottom plate. We will exploit some kind of symmetry on one of the sides here, so we will reduce the domain by half. um, yeah, and in this case we'll use a harmonic balance method as shown by our CTO Alexander. And in this case I would use first three harmonics. Will have mesh deformation included, geometric nonlinearity, and also pre-stress included in this case. So let's move on to the product itself. So here I have built the geometry already. So you can see two plates separated by air gap. I will show you how this can be built. For example, in this case I also tried to take advantage of shared expressions. So this means that we can define the geometry. um, so basically length, um, here 1000 micrometers, width, and thickness of one of these plates, and the air gap, frequency and voltage, and I could parameterize my geometry based on these dimensions, as you can see here. And yeah, once I have the geometry, then I could define different materials. So for example here, I've chosen air from the materials library and also the monocrystalline silicon. One thing to highlight here is we can easily do anisotropic material properties. For example here, elasticity matrix for silicon, because this is monocrystalline, and for this there is strong anisotropy expected. Then I can define several regions which are interest or which are required for defining the interactions or boundary conditions. These are not necessary but helps in some way to tagging the domains with some physically meaningful name. Uh, yeah, once that properties are defined, um, this is the part, or this is the menu where we define different kinds of physics here, excuse me. So in this case, we have four kinds of physics involved, or four types of physical processes involved. First is laminar flow, which is in the air gap. Then solid mechanics, which takes care of the deformation of the top plate here. Then electrostatics, which is supplying the force. So uh, having the voltage across the gap produces the electrostatic force acting on the plate, top plate. Then mesh deformation, because the mesh, so as the top plate deforms, so the domain or the air gap has to be squeezed, and we have to tackle the mesh deformation there. So let's go through one by one these physics and how they are coupled. So laminar flow, we have to define the no slip boundary conditions for the boundaries where we expect the flow to be static. So these are the so basically we can just try to hide some regions here. So as you can see, uh, so on the bottom I have assumed that there is no air gap, so that's why there is the no slip boundary condition on the bottom plate, which is static, also no slip, and this is on the side of clamp. So three boundaries chosen as the no slip boundaries. And yeah, and outlet, so this is the outlet where the air should move in and out. Then beam wall is the wall where basically that's the that's the boundary which will be interacting with the air. So this is the moving boundary basically. And the symmetry, so symmetry on this side, because we don't want to simulate the whole domain in this case. Then let's move on to solid mechanics. So we need to clamp one of the uh, uh, one of the sides here. So as you can see here, then clamping the bottom plate, then the way the electrostatic force is applied, and yeah, the large displacement that is included for the mesh deformation in this case. um, Before I go to electric force, maybe to include the electrostatics. So in this case it's very simple to apply the voltage. You select the volume, so target plate in this case, which I have already defined here as electrode target and the ground target, and these are basically chosen here. And on top plate I apply the cosinusoidal voltage with some amplitude and set the ground to 0. And once this is done, you can select from here the electrostatic force as the interaction between solid and electrostatics, and that applies the force on the top plate. And for the mesh deformation, we apply we include this as a physical process and apply the constraints on the solid domain, that the solid should move along with the mesh. I haven't described how we couple the laminar and solid mechanics. We'll describe in later in the script mode. Uh, s- yeah. So let's move on to simulations. So in this case, we can create several. So in this case, we have to first create the mesh. We have to highlight this here. So we have structured measure available for these kind of simple geometries. You can easily create such nice rectangular mesh. And yeah, let's move on to simulation. So there are several simulations I have already run, and I would like to focus on one of them. So I chose one of the case from the paper which has voltage of 31.7. There is no reason for choosing, just chose one of these and tried to simulate it. Chose the analysis type as multi-harmonic. As you can see, four types of physical processes. uh, Frequency defined in the shared expressions, so that is easy to do frequency sweep. And as Alexandra described the harmonic, so first harmonic, um, 2 and 3 are these harmonics at the first fundamental frequency, and the 4 and 5 at the second or twice the fundamental frequencies. um, yeah, and ran this on 48 cores, and so on. So let's try to first look at the script. For this case I had to add some additional measures, so to for example, to describe the or to tackle the mesh deformation in this case. So I got the auto generated script first, and then I could add simply a few expressions which we need for mesh deformation. So before I go into those, let's have a look at what's the idea behind that. So in this case, to tackle the mesh deformation, I take an example of electrostatics. So as you can see, the weak formulation here, the first equation, there is gradient of electric potential. uh, uh, it has been integrated once, so that's why you see yeah, grad of electric potential and the electric permittivity in this case. And you can see the star, which means that this is on the deformed domain, as you can see on the right hand side, and we have to bring it to the undeformed domain uh, by using some Jacobian transformation. So in this case, as you can see here, the from going from the undeformed domain to deformed domain, we have to use Jacobian transformation, and inverse is also shown here. So uh, if we do this mathematically, you end up with the expression or the equation at the bottom here, where the gradient introduces inverse of Jacobian, and the because of the volume integration, you have this determinant of Jacobian involved here. And once we understand, we have these equations, we can go back to our script. uh, we have to define additional field, which was already defined when I introduced the mesh deformation physics. And what I have to do here is to calculate the Jacobian like this. So simply take the gradient of the deformation with respect to um, the physical space, and then compute the inverse. It's just function, you can use inverse of Jacobian and the determinant of Jacobian. Once I have this, I can uh, go through the equations, and for example, I can compute grad v simply by grad v times J inverse, and transpose operations are done to take care of those mathematical transformation. Yeah, and similarly, I mean, these operations have to be done for the laminar flow as well, which have been added here, not to scare you away, but yeah. So this is not that complicated as it looks like. And let me go to the electrostatics example. So yeah, so as you can see, I have defined here the first grad, which is the degrees, so unknown variable, and the second is for the test function of the electric potential, and we can simply add this integral, which is grad of v times grad t test function v, and multiplied by determinant for volume integral. And that's all for the electrostatics example. Yeah, not that's not all. We have to also do for electrostatic force here, but yeah, I won't go through details of that. Another thing I wanted to explain here was the coupling between the laminar flow and the solid mechanics. So in this case, we implement this by enforcing the velocity at the interface to be the time derivative of the displacement. And as we enforce this boundary condition, we naturally get the force balance between the solid mechanics and solid domain and the fluid domain. And this is added by these two lines. In addition to that, as I said, we also include geometric nonlinearity and pre-stress. So it's easy to add pre-stress here. We just define two lines of code, and um, yeah, we have to include the pre-stress as the argument, and that's it. And once we have done all of that, the last thing, which is auto generated, is to tackle the deformation of the mesh itself. So as we deform the mesh, so the nodes are redistributed smoothly using a Laplace solve for the mesh deformation field in this using this. So this wasn't added by me, this was auto generated. And yeah, once that is done, we are ready to solve. And yeah, as we solve I have here pre-solved example, and you can take a look at logs. We have 800,000 degrees of freedom, and it takes about 15 iterations to solve, and about 1,000 seconds. So that's about 15 to 16 minutes, I guess. And yeah, once we have the solution, uh, let's look at the results now. So that's how the results look like. So I exported the time. So I extracted, so the result that we get, simulation results, we get harmonics, and we have predefined functions to export this as a transient, let's say um, transient files. And that's what I have visualized here. So the top plate, which is deforming harmonically, and as it deforms, it squeezes the air between, and you can see on the bottom left is the section at the center of this plate, and you can see the flow moving in and out. And this was done for frequency of 100 hertz, 800,000 degrees of freedom, took about 30 minutes on 12 cores, and full this includes all physics fully coupled, and yeah, electrostatics, solid mechanics, and fluid dynamics. That's the qualitative comparison. Let's have a look at the quantitative comparison. So here what I plot is the displacement, normalized displacement along the center of the plate. So going from left to right here in the center of the top plate, uh, only until the only because we did symmetry example, so that's why it's cut at 500 micrometers. And here you can see the orange plot from the paper, which is measured data, and on top of that is blue curve, which is from the quansa and all solved. We can see that the displacement is slightly over predicted, but that could just be because of the mesh, or yeah, because I didn't use sufficiently fine mesh probably. So yeah, I mean, this we would consider a reasonable match in this case. um, yeah, so that's all from my side. I would hand over to Yuka.